Let's get started on chapter 4. Chapter 4 is on determinants, which you probably would have seen before by now. So in 4.1, it's all the review stuff that you would have seen in Calc 3, area, volume, cross product. We wouldn't be really doing anything specific in the class with that stuff. I did assign homework, so you can try the homework or get through, just do a few of them just for your own sake, your own review. Probably won't be really looking at it, but get started on it. So let's go ahead and get started on 4.2. I'm going to show you the little bit of the theory, or initially the simple concept of a 2x2, a little bit of the theory, and then we'll get into the properties. The section is not really about taking determinants. It's more about the properties. So we'll get more into that later. All right, so the determinant of a matrix is what we want to look at. So historically, you can look at something like this. You would have had some sort of equation like that, and then say dx plus ey equal to f. And you can calculate and show that the solution is, if you just did the normal operations, you can show that the solution for x is CE minus FB over AE minus DB, and y is AF minus DC over AC minus DB. And note this is a C. Nope, sorry, that's an E. That's an E. And note that these denominators are the same. That is, of course, provided that the denominator is non-zero. So you would say AE minus DB does not equal 0. So this pattern came from the general solution to a 2x2 system. The value AE minus DB is called the determinant of the coefficient matrix. So the coefficient matrix A would be A, B, D, E. And you've probably seen that calculation. We say that the determinant of A is equal to the determinant of A, B, D, E. And you multiply basically across A times E minus B times D. So you get AE minus DB. So that basically was noticed that the solutions have this pattern. That's how it was kind of built, essentially. So you can write, looks like absolute values around the matrix, or you can write determinant of A like that. Either way is done. Okay, so let's do another example with actual numbers. So this is just a 2x2. We take the determinant of 2, negative 3, 1, 5. Then you get 2 times 5 minus negative 3 times 1. Be careful of your signs, and you will be able to use the calculator doing any of these determinants, so don't really worry about the actual calculation. 10 plus 3 is equal to 13. So the determinant becomes like a tool. It's like an operation. It's like multiplication. Multiplication in and of itself, you can just do it, but it's used for quite a number of things. Same kind of thing with the determinant. You can just take a determinant for the heck of it, but it's actually used for quite a number of things. So now a little bit of the theory and expansion we'll use. We're going to do this so we can at least have a discussion about some of the properties of the determinants and the proofs. So a definition of minors and cofactors. So this is how it's defined for minors and cofactors. So if A is a square matrix then the minor and we denote it Mij of the element Aij, so that's like some particular value like the 5 up here, like that would be A or Aig. The minor is something else. So is the determinant, and I'll start abbreviating, is the determinant of the matrix obtained by deleting the ith row and jth column of A. Ith row and jth column of the matrix A. So you get so it's basically another matrix. The cofactor Cij, so it would be corresponding to Aij. So Cij is given by Cij equal to -1, and then it's raised to the I plus j, and then times ij. So the cofactor allows you to put in that the -1, and you basically add the whatever row and column you're in. And this is what creates, when I do college algebra, and I'll tell you here as well, what you do is a sign chart. So if this is a 3 by 3, the plus or minus of this corresponds to a sign chart. So 0, 1, 0, 1, or I'm sorry, I did that wrong. Of course I did. It's 1, -1, 1, -1, 1, -1, 1, -1, 1. That's not how we usually write it. That's correct, but I usually just do plus minus. That's why I was hesitating. Usually just say plus minus plus, minus plus minus, plus minus plus. And those you can think of those as -1s. That'll correspond to that I plus j, and you can just use a sign chart like that. We'll talk about that more, but I do want to get into the minors and cofactors again for nothing else, so we can help follow the proofs a little better. So let's take a look at a arbitrary but specific example. We'll do a 3 by 3. So let's take a 3 by 3 matrix A, B, C, D, E, F, G, H, I. Like that. So we want to calculate minors and cofactors. So we'll do a couple examples. So if I do M21, that's not 21, it's 21. So M21 would be it's like you're doing the determinant of that matrix. I think I said it's obtained by, it says determinant. I said that right. Is the determinant of the matrix obtained. So 2-1, it's always row by column. And that's stuff I wanted you to review. So just kind of coming back here, maybe, I don't know. It's always row by column. It's always N by M. So this is a 3 by 3 matrix. So the minor would be 2 by 1. So it's 1, 2. So you're in the second row and the first column. So it's talking about D. So you take out, or you do this essentially. You cross that out, and what's remaining? What's remaining is B, C, H, I. So that's your minor. And let's go ahead and get rid of that. So we can do it again. And so try this one, M13. Into the determinant of, so do that one. So first row, third column. So first row, third column. And so what's the remaining matrix? You see there is D, E, G, H. Let's get rid of those again. And then let's calculate the corresponding cofactor. And we'll do it using the formula basically. So C21 is going to equal, and do -1, and you just add those up, 2 plus 1. So it's going to be negative. And then it's M21, which is above. So it just tells you what sign that's going to be. So that sign is going to be negative. So it's negative M21. So if you use the sign chart I did on the side there, you get the -1. It's, where were we again? So 1, 2, and 1. So this one, this D, corresponds to that negative, which is this negative. Okay, so either way. All right, let's do another one. Let's try this one. C13. Negative, so try that. Pause it. Okay, now go. It's -1, and then it's 1 plus 3. And then it's M13. And that one, well, it's 4, so it's positive. So it's M13. So it's that determinant. So what do we have? So 1, 3, let's do this again. First row, 3, so right here, that C, that should be positive. Yep, it's positive. Okay. Let's do an example. So find C23 of the matrix A. We'll come down back over here. Matrix A will be A very simple matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's do that calculation. C23 is going to equal negative 1 raised to the 2 plus 3. Kind of makes that easy, right? So that'll be negative. Then it's times the determinant of, and so you cross off the row and column that you're in. So row, so 2, 3, so 1, 2, and 3. So what's remaining is your determinant. 1, 2, 7, 8. And then we can do that actual calculation. That's negative, and then it's times 8 minus 14, which is negative 6. So it's negative 6, which is 6. So that cofactor is 6. Okay. Let's go ahead and do the definition then. So definition of a determinant of a square matrix. We say determinant of A and we'll make that n by n. Or we can write determinant of A like that is equal to, and we say the sum as j goes from 1 to n, A1 j C1j. So this would equal, can't keep it from doing that for some reason. That's going to equal A11 C11, and then you would continue. So it's A11 C11 plus A12 C12. Now this is assuming you are expanding on the first row, which you don't have to, which we'll talk about later. So, I actually did write that down. So I said note the definition expands, is what we say, on the first row. But it doesn't have to. That's one of the theorems. They have a proof in the appendix. We won't go through that. It's kind of tedious. So let me show you how to calculate that expansion. So you won't have to even calculate these on your own, but it's good to know, try to study what this is saying, because we will go through some of the proofs of these, but not really all of them. So calculate the determinant of A if A is equal to negative 3, 0, 0, which will help a lot, 7, 11, 0, 1, 2, 2. All right, okay, call that a matrix right now. So first we will expand on the first row. Like they'll show that. And then maybe we'll show that it's, well, maybe I'll just have you do it. You guys try it. You all try it on a different row or column. And you do the same process. So the way I usually do this, and I'll do it kind of both ways right now, trying to go slow here. These notes might be a little clunky, sorry. Maybe not. Maybe it's all worked out nice and I can't tell right now. I'm working too much. Do a sign chart. So you do plus, always start in the upper left is plus. So plus, minus, plus, minus, plus, minus, plus, minus, plus. If you do this sign chart, then you know what those cofactors are. The minor you calculate by crossing it out. So that's really how you want to do it. So you do the determinant of A equal to, and so you look at the sign. So here's the sign. This is your first entry, the -3. That's this right here. So it's positive -3. So you just say -3 times the determinant. So what's left in that determinant, and I'll highlight but then erase. So it's that. So what's left is right there. 11, 0, 2, 2. And then it'll be a minus, and then what's next is 0 times the determinant. And I'm going to put this in this time, even though it's 0. So the next one would be here, 7012, which of course you don't have to write, correct? Because it's 0 times what, it's all going to cancel out. Then next you have a plus, and if you check the cofact, the C's, that's the sign. So 1J, if you do that, you'll get the correct sign, of course, and the minors and all that. So you're figuring out the minors. So it's a plus 1, and then times 0, and again, times the determinant. And I'll erase that again so that you're highlighting this or crossing that out. What's left is 7, 11, 1, 2. And I'll go ahead and erase that again. So do that calculation and you get -3, and then you're doing 22 minus 0. So that would be -66, it looks like. So what I want you to do next is expand on any other row or column. So do the same process and use the sign chart and see if you get -66. Let me make sure I did that right. Those are all zeros. 2 times 11 is 22. 3 times 2 is 6. Yeah, okay, we're good. Just double checking. All right. Okay, so try that. I'm not doing another one. You try it. You can verify yourself. A couple definitions. Let's do triangular matrices. Triangular matrices. So these are kind of special cases. We have, and I'm just going to give you examples. I'm not going to get all careful, detailed yet. We'll do a couple rigorous style proofs later, but not tonight. So upper triangular looks like this. So upper triangular, basically the bottom are zeros. So if you have like 1, 2, 3, 0, 4, 5, 0, 0, 6, and that would be upper triangular. And then you have lower triangular. This is basically the other way around. 1, 0, 0, 2, 3, 0, 4, 5, 6, So that's lower triangular matrix. And you can kind of guess where that's coming from, like this. Upper, this would be lower. Then we have, so there's some specific properties of determinant we will go over with that one. And then we have diagonal. So diagonal matrix. This one we use quite a bit too. So basically, zeros elsewhere. So 1, 0, 0, 0. Oops. Say 2, 0, 0, 4, and then oops. Do that again. That's supposed to be a 0. And then say like -3 or something. So there's the diagonal has values in it, non-zero values. Usually, I think you would need to say like at least one is non-zero. I mean, otherwise they're all zeros, which is kind of not very interesting. So that's one case. Okay. The next would be getting to